approaches for market integration and price transmission of agriculture commodities. This lecture will be delivered by Dr. Purushottam Sharma. He is a principal scientist at ICR NIAP. He has about 17 years of experience in different organizations. AgriWatch, National Institute of Agriculture Marketing, Jaipur, Indian Institute of Soybean Research, Indore, and ICR NIAP. And his area of expertise is commodity futures, commodity marketing, trade, agriculture marketing, technology impact assessment, and climate change. And the topic is very important for today's this session. And now I request Dr. Purushottam Sharma sir to please deliver this important lecture to our participants. Sir, please.
Thank you, Dr. Vikas.
Thank you, sir.
And good afternoon to all participants. I think I'll try to share my screen. It's visible?
Yes, sir.
Visible, sir.
So today we are going to discuss on market integration and price transmission. Any participant, if they can tell about what is the market integration, how they perceive the market integration and how it functions. Anyone can help me. I hope everyone has undergone course of agriculture marketing, and in that there is a topic on market integration. So if you remember, see, two spatially separated markets, two or more spatially separated markets, or temporarily separated markets must be integrated to or follow a long run equilibrium process. How it functions or how it happens, we'll try to discuss. For that, what we are going to do in this 1.5 hour session is we'll try to understand theory of market integration, how market integration works, and what are the factors in that. Then we'll try to understand the trends, whether it is deterministic or stochastic, spurious regression, whatever we go for the regression analysis, there may be a spurious regression, how to detect it, and what is the role of time series in that. And then we'll see the concept of co-integration steps, how it is tested. Then error correction, we'll try to work on the degree and the speed of adjustment to the long run equilibrium. And all those will try to work on in R. I think this is a free software and everyone has undergone class on R. Dr. Vikas?
I'm getting, sir. Yes, sir.
Okay. So it will be easy for them to understand whatever codes we are writing on R and how we can do market integration and price transmission analysis in R framework. So we will try to divide this in half a part around, we will do theory part, and then we will work in R. And we'll see. I'll send 2 files to Dr. Rajni. I think she will send to participants. So they can, when we are working on R, they can also come along with us. Okay. So, yes. So agriculture prices in either separate means spatially or temporarily separated markets should adhere to the long run equilibrium or the co-integration relationship. How it happens, that we will try to understand. Suppose I will take an example of 2 markets for soybean. Suppose Indore and Ratlam. Prices of soybean today in Indore market is, for example, 5,000, and price of soybean in Ratlam market is 4,200. So what does it mean? It means either supply is high in Ratlam market or demand is less. And conversely, supply is low in Indore market and demand is high. That is how prices are high in the Indore market. So what an intelligent player or a trader, what he will do? What he will try to work out the cost of transferring this commodity from Ratlam to Indore. And suppose that cost comes to 300. Okay. So in that case, it comes to the total cost would be around 4,500. So what he will do, he will buy at Ratlam market and he will try to sell at Indore market at 5,000 rupees, whatever the case may be. So this way, he is trying to create demand in the Ratlam market and he is trying to increase supply in the Indore market. And with this function of this, and this function is called arbitrage. And with arbitrage function, the two markets which are in which the price of a commodity in at a point of time there is a discrepancy. So with the act of arbitrage, the discrepancy in two markets would be reduced and the price will come to an equilibrium position. Okay, so that is how this market arbitrage functions, and due to this arbitrage function, the markets are integrated, I would say. So any shock or any change in demand or supply situations in one market, through arbitrage, they are transmitted to other markets also. So price transmission will be perfect between locations and time periods with the help of arbitrage situation. Without integration, there is no mechanism by which excess demand or supply changes may be transferred spatially or temporarily. The example we have discussed about Ratlam or Indore market for soybean. Similarly, that can happen in temporarily separated markets like futures. Spot price and futures maybe 2 months down the line or 4 months down the line. The contracts which are trading maybe now April contract or June contract. So that same arbitrage function from spot to futures also is possible. So no price shocks are shared between non-integrated markets. If markets are not integrated, the price shocks are not shared between the markets, and if this happens, we say that markets are not integrated. So this is brief about market integration, and all theory revolves around this. So we'll discuss how it happens and how we can test it. So theoretically, we will try to understand all those. But before that, we'll try to understand the nuances of or the particularities of time series. Everyone in economics or in social sciences, we do regression analysis. Maybe to test the validity of economic theories, maybe like consumption function, we say that consumption is the function of income plus error. So suppose we have one variable. So consumption is the function of income and plus error. So through regression, what we try to understand is try to see the what is the whether our economic theory is validated or not. So the coefficients between we are trying to estimate the relationship between the variables and test our hypothesis. So in this case, we have particularly like in time series, we have the data which are time dependent. So the basic thing is the variables are stationary. Assumptions of this regression is variables are stationary. Errors have zero mean and finite variance. Okay, so there should not be any pattern in errors. That then only our theory works, and then only our regression if it is normally distributed. So a series is said to be stationary if it tends to return to its mean value and fluctuate around its within almost a constant range. Maybe either if it is trending, it will fluctuate around mean. Maybe it is like this, fluctuate around mean. And there is the variance is also constant. And shocks to a stationary series are temporary as against non-stationary series. So in non-stationary series, shocks doesn't transmit to other markets or other variables. And that's how the peculiarity of this is a peculiarity of this time series analysis particularly. Any macroeconomic or financial time series are mostly non-stationary in nature, has a different mean at different points in time, and its variance increases with the sample size. So it will not revert to a long-run equilibrium level. And hence we need a new approach to deal with regression involving a non-stationary time series. So now we will try to understand the trend what we have discussed in previous slide. Trend may be of two types, and a series may is a realization of both stochastic trend and a deterministic trend. Okay, so a non-stationary series which can have a trend, and it composed of two types of trend, deterministic and stochastic. So stochastic is a random trend, varies over time, whereas deterministic is non-random function. It is a non-random function of time. So it increases or decreases, whatever the case may be. It trends with the time, like this one. Though mean is changing over the period, and that's how this trending up in the market. Okay, so if we see the deterministic trend, it is a function of time, and this ui or the whatever we say is the error term we say is represents the autoregressive and moving average process, which is independently and identically distributed. The another is stochastic trend, and in that we have two types of either random walk and random walk with drift, or with a constant, what it says. This one constant and depends on the previous value. So again, this kind of trend we say is, this one is a random walk and this one is a random walk with drift. So a trending mean is a common violation of a stationarity. And to model a time series, we need to test for the stationarity of the data series. So this time series variables can be made stationary through two methods. One is trend stationary and another is difference stationary. If the data is trend stationary, what we would do, we would regress the series on time. Okay, and then the trend is removed from this data through residual, and we take the residual series, and that residual series is stationary stochastic process. So that is one method. If it is deterministic, the trend is deterministic in nature. If trend is stochastic one, we generally differentiate the series, and in that part, this one is with the drift, and this one is your combination of or accumulation. Your error is accumulated over time. In both these things, both these random walk or random drift, error is accumulated over time. So differencing the series with the previous one, or maybe one time or two time, we make the series stationary, and then we use the series for further modeling. So a key feature of trend is that it has a permanent effect on the series. And if a variable is made stationary by differencing d times, then it contains d unit roots. And it's said to be integrated of order d. Suppose if we differenced series by previous one, so it is of order 1, single order. Okay, so the way the time of differencing makes it the order of integration, or unit roots, whatever we say. And this distinction between deterministic and stochastic trend has important implications for long-run behavior of the data generating process. So time series with a deterministic trend always revert to the trend in the long run. The effects of shocks are eventually eliminated, and forecast intervals have constant weights. While time series with stochastic trend never recovers from the shock to a system, the effects of shocks are permanent, and forecast intervals grow over time. So that's the beauty of this trend kind of thing, and we have to know that whether our data is trending. If trending, then what type of trend is there, stochastic or deterministic. Then we go about the spurious regression we discussed initially. A non-stationary time series variable cannot be used in regression analysis, as these may result in spurious regression or a false relationship, as proposed by Granger and Newbold in 1974. In their analysis, they said that for a time series variables which are non-stationary, you can't go for regression. If we regress to non-stationary time series, then it will give a false relationship. So spurious regression, we will try to understand through example also in R. But this phenomenon where one often obtains a very high R square, maybe excess of 0.9, and low value of Durbin-Watson test, even though there is a no meaningful relationship between two variables. Maybe you can get a significant variable as a significant and high R square, and you may conclude that there is a relationship between the variables. But since the data are non-stationary, your regression coefficients may be a spurious one. And that if there is a rule of thumb, if R square is greater than Durbin-Watson test statistics, your regression model is spurious. So we'll try to see in the next slide. Suppose we regress YT on XT, and both these two are independent series. Independent and non-stationary, their error terms are independently and identically distributed with the mean 0 and constant variance. So the coefficient which I worked out from a randomly generated series is the beta coefficient for X1 is 1.4, and which is highly significant. R square is close to 1. Durbin-Watson statistics is 0.03 or close to 0. So this shows that there is a high degree of autocorrelation in the estimated coefficients. So this is the case of spurious regression, and one must be cautious while using the regression of a non-stationary time series in this way. So what is the way of handling this spurious regression? Either detrending, as we have discussed, or differencing. So detrending presents, if deterministic trend is present in the data generating process, then suppose by T, we will regress on T and we'll try to eliminate or remove this trend from your original series. Then it will be a stochastic series. In differencing, if there is a stochastic trend, differencing diminishes large positive residual autocorrelation, and thus false inferences could be drawn on the regression coefficients can be eliminated. Economic theories are formulated for levels of variables rather than for differences of variables. That is a major issue if we difference the data. So dynamic models based on linearly detrended or referenced variables will also remove the long run relationship. So what to do in that case? Then we have different approaches and methods of testing co-integration, which takes care of all this time series issues, which we have discussed earlier. So empirical research in market integration used different quantitative techniques to test market integration and price transmission between different markets. One is co-integration, then causality, symmetry, and error correction mechanism. So the co-integration or the market integration, which we have discussed, suppose there are two markets, P1T so this is a relation which if we are going to test, then these are two spatially separated markets and price, or we can say prices of commodity into specially separated markets. So the law of one price or LOP, which we are going to test, says that at all points of time, if the transfer cost is allowed, the prices in these two markets move, or the commodity in these two markets move from market A to market B through arbitrage function, or arbitrages takes care of that. And if such a relationship is there in these two prices, two markets are said to be co-integrated one. So we'll discuss all those one by one, and I think we'd try to discuss co-integration, causality, and error correction mechanism. Symmetry will try to omit because of lack of time. So co-integration is proposed by Granger in 1981, and he defined the concept of degree of market integration, of degree of integration of variables, particularly time series variables. If two or more non-stationary time series, that is called I1, as we have discussed in this one, the order of integration, are I1 or integrated of order 1, we say these are co-integrated if there exists a linear combination of them that is stationary. So two or more non-stationary time series integrated of order 1 are co-integrated if there is a linear combination of these two time series, which is stationary, or I0. And we will try to test in our example also. Suppose both X and Y are I1. Generally, a linear combination of two will be I1. In general, whatever we go for regression. However, if there exists a vector B such that the disturbance term from the regression or this is I0, then two series are said to be co-integrated. This is the theory of co-integration, which we are going to test in our practical example also. Many time series are non-stationary, but they move together. Or what we say is the co-movement of the two time series over time. If variables are co-integrated, it means a linear combination of them will be stationary one. They will not drift apart, maybe like this. So there is a co-movement of the prices. And suppose if this is kind of, so this is drifting away, and there is no or very less kind of integration in this kind of series, while there is this series is kind of this type of series is co-integrated or integrated as they move together or co-move over the time. So co-integration relationship may also be seen as a long-term relationship or a long-term equilibrium relationship. Market forces arising from no arbitrage conditions should ensure that an equilibrium relationship. So if there is an equilibrium relationship, there will be no arbitrage condition. And if the series violates the equilibrium, or there is any demand or supply shock for time being, then this arbitrage will take care, and then price will try to come to an equilibrium position. So if there is no co-integration, that implies that the series wander apart, the difference will further diverge in the long run. So two non-stationary time series or I1 time series with a long run equilibrium relationship cannot drift too far from the equilibrium, because economic forces will act and they will restore the equilibrium relationship. Any linear combination of this vector of betas is often motivated by economic theory and referred to as a long run equilibrium relationship, which we are going to test in our practical example. So there are two kind of situations or tests we are going to cover in this cointegration analysis. There is one cointegrating vector, or what we say is bivariate cointegration, bivariate modeling. So Angel and Granger, they proposed this in 87. They developed a simple two-step residual based testing procedure based on regression techniques. And there is another, if there are number of markets rather than only two, we want to see the integration in more than two series or more than two markets, maybe 5 or 10. Then there will be R cointegrating vectors. So for that, there is a Johansson methodology. Johansson proposed in 88, and he developed a sophisticated sequential procedure determining the existence of cointegration for determining number of cointegrating relationships based on maximum likelihood technique. So both these tests we would try to understand. So in nutshell, what we have discussed, if the Y and X are non-stationary and non-integrated, whatever model you fit is regression model you fit is a spurious regression, and there is no any relationship captured. If Y and X are non-stationary but cointegrated, non-stationary but cointegrated, we have a cointegration model, and the relationship long-term relationship is captured through modeling. Y and X are stationary, then regression model and only short-term relationship is captured. But if Y and X are cointegrated, then stationarized YT can be regressed against stationarized XT, and we can go for error term of the cointegrated model. Then error correction model we are going to put, and both long-term as well as short-term relationships we are going to capture in that. So the steps which we are going to follow is we are going to test the raw series first. Maybe 2 or 3 or 5 or 10 series are there. We are going to plot it, and then we try to see the unit root test or stationarity test. If series is all the series you are going to analyze are I1 or what we say is difference stationary, then we will go for cointegration tests with P-1 lags. If all are I0, means stationary at levels, then we are going to go for var-in levels, and lag order will be defined based on this bar. Third case is if some series are I0 and some are I1. Maybe 2 markets are I0, 3 markets are I1. In that case, we'll go for ARDL model, autoregressive distributed lag model. Okay. If I1 series or 2 non-stationary series, we test for cointegration. And if there is a R cointegrations between them, then we'll go for vector error correction with P-1 or R cointegration. If there is no cointegration between them, then var P with P-1 in differences. Here in levels, here in differences. So that's the difference what we have to understand. So we'll try to see both the approaches of cointegration. One is to this bivariate, which we have discussed, this one, bivariate one, or R cointegrating vectors. So both these we will try to understand. So as Angel Ganger proposed, a 2-step method to test or determine the long-run equilibrium relationship in 2 or more variables. So this can be done, and the step 1 involves, first is to pre-test for the order of integration. Pre-testing is required. Okay, because which model or which method we are going to adopt depends on this only. So make sure that all the individual variables are I1. If all are I1, we will go for integration test, co-integration test. If all are not I1, then we will, or all are stationary at levels, we will go for var. Then estimate cointegrating regression using OLS, or we say that long-run equilibrium relationship. Third step in this is save the residuals of cointegrating regression and then test the residuals to ensure that they are, residuals are I1, I0. So this is the one step. And then second step, use these residual series and this as a variable in the error correction model. We are going to test, and this error term, what we say is must be identically and independently distributed. So after that, we'll try to assess the adequacy of the model, whether the model is adequate, normally the error is normally distributed. So what all those things we are trying, we will try to work out. But the first step, which is pre-testing, and there are 3 methods: augmented Dickey-Fuller, Phillips parent test, and KPSS test. So non-stationarity we have discussed. There is a constant mean, constant variance, and covariance between observations do not depend on time. They only depend on the distance or lag between them. Okay. So thus, if any of these conditions does not hold, we say that YT is non-stationary. There is a no long-run mean to which the series returns, or economic concept of long-run equilibrium, what we are going to test. Then variance is time dependent. For example, that could go in infinity as the number of observations go infinity. And theoretical autocorrelation do not decay. So autocorrelations plot, if we go for that, so if it should decay over time. If it doesn't, then series is not integrated, or unit root is not there. So we are going to estimate, and then second is estimate long run equilibrium from this YT and XT of this I1 series. Okay, you need to, from that, generate a residual series, test for stationarity. The variables are integrated if the residual series generated from fitting above regulation turned out to be stationary one. The residual series, if it is I0, then we say that these two variables or two time series are co-integrated. Then estimate error correction model. Error correction model, as the name says, is whatever error or shock in the series is how whether it is corrected and what time, degree, extent it comes to an equilibrium. So if X and Y variables are co-integrated, residuals from the equilibrium regression can be used to estimate error correction model. In this case, co-integration provides evidence of long-run relationship, and while ECM provides evidence of short-run dynamics of co-integrated variables toward long-run equilibrium. So how long it takes to adjust to the long-run equilibrium, or to what extent or to what degree it is adjusting. In this say this is error term, and this error correction term coefficient, as per theory, it suggests that it should be negative, whose value measures the speed of adjustment back to the equilibrium position following any exogenous shock. So this is the position where long-run equilibrium we are going to test, and then this one is the short-term shocks or the error which is residual from the co-integration relationship, which how long it takes to adjust to the long-run equilibrium. Any error correction model which includes I0 variables. This requires all our non-stationary variables to be first difference to produce any stationary variables. And error correction term is if there is a co-integrating relationship lagged one over time period, that too will be I0. Then only we say that there is a co-integration. So error correction model which can include a number of lags on both the variables. Both sides we can include lag variables based on the where we say that how many lags are required. Then it models the short-run dynamics of the model, which comes to the long-run equilibrium model. So it is necessary. See, co-integration is a necessary condition for modeling ECM or vice versa. That is again as per the Granger representation theorem. And the coefficients should lie between 0 and 1. Alpha coefficient should lie between 0 and 1. 0 suggesting no adjustment in one time period, and 1 indicates full adjustment. So if it is larger, this coefficient is larger, then adjustment is faster one. Okay. So just to show an example, I have taken two price series, Indore and Ujjain market for soybean. Soybean prices from January 2006 to December 2020. And it has been sourced from AgMarkNet, which I sent to, maybe you have got in your mail. ADF test, as we have discussed, pre-testing is required for unit root test or stationarity test. So we have tested it for stationarity, and code for this is ADF. Okay, ADF Indore I have taken. So again, this decufuller or augmented decufuller test or stationarity test, which we can have of three types. Whether there is any drift in the series, drift and trend present in the series, or there is no drift and no trend in the series. Okay, so if we see, there is Indore is the level series without any differencing, and if we test the test results show that this series is non-stationary one. Null of stationarity is rejected. So we go for difference stationary, and code for this is Indore difference through diff Indore. Okay, and again same, but the variable here is difference one. Okay, now we see that the series is stationary one. So we can conclude that our series is stationary at one level of differencing, or it has a unit root, one root in that. Okay. Then Granger casualty, so Angel Granger cointegration test, we will also see that for Indore and Ujjain markets, Indore equation will we try to regress both way, Indore on Ujjain, Ujjain Indore. Okay, we'll try to see what happens, whether Indore, Ujjain affects Indore, or Indore affects Ujjain, or what happens there. So we regressed Indore as a dependent variable and Ujjain as an independent variable. Then error series we have generated. This is a code for residual. So residual series we generated through that for both Indore and Ujjain. So from Indore equation, we generated error series for Indore. From Ujjain equation, we generated error for Ujjain. Okay, and then cointegration, we have seen whether these are cointegrated one. So this shows that the result shows that these are cointegrated. As we have seen in our steps, we have pretested, estimated long run OLS regression. This is long run OLS regression for Indore, for Ujjain. And then we have saved residual series from the cointegration regression. So this is the residual series from this regression. And then we have tested for stationarity of the residual series. Okay, and this is clear that these two series are cointegrated. But error correction may give different results. So we tried to work out error correction of the Indore and Ujjain separately. So error Indore as variable we have taken, error Indore and error Ujjain. In both way we did it. Error correction we did for Indore, taking Indore and Ujjain lagged values, difference values, lagged one. Similarly for Ujjain, and these are the results. So this is error correction term, what we have seen here. This error correction term, and though results show that it is negative, what we have seen, error correction coefficient should be -1. but the thing is, error correction term for both Indore and Ujjain is not significant. So we will go for Johansson one method, and Johansson cointegration is a multivariate approach in which we can take more than 2 variables, maybe 5 or 10 variables also, which Johansson method uses maximum likelihood procedure, and it is possible to obtain more than a single cointegrating relationship in one, or a vector of cointegrating relationships at a time. So if there is evidence of more than one cointegrating relationship, which one should be used? That says that we have to look at. If there are 2 separate tests for cointegration, one is trace statistics and another is maximum eigenvalue statistics. So given that this is a maximum likelihood based test, while Engel-Genger was OLS based one, it requires a large sample. And multivariate test is based on VAR, not on a single OLS estimation method. All the variables are assumed to be endogenous, although there is a possibility to include exogenous variables also. The test relies on relationship between rank of matrix and its eigenvalues or characteristic roots. Based on rank of matrix, we are going to say whether how many rank are significant one. So okay, we'll try to fasten. So our rank of cointegration is based on this, that determines the number of cointegrating vectors. If R is 0, there is no cointegrating vectors. If G variables in a system of equation, there may be a maximum of G minus 1 cointegrating vectors. Okay. I think we are not going to discuss much about it, but there are 2 types of trace statistics. One is trace and another is eigenvalue. We'll see it practically also. Both these can determine the number of cointegrating vectors present, although they may indicate different number of cointegrating vectors, which we have to decide on. For that, I have taken again 3 series, Ujjain, Indore, and Devas, and then tested for this Johansson cointegration. And here it says if your test statistics is greater than 5% critical values, we reject this, and we're going to say that there is more than 0, means there is at least 1 cointegrating vector in that. Similarly, this says that there is more than 1 cointegrating vector. There is at least 1 cointegrating vector in the series. But here it is less than that. We cannot go beyond that. So after that we can go, if the series is cointegrated, then we can go for error correction models, as we have seen vector error correction. These are basic VARs with an error cointegration term incorporated into the model with a bivariate cointegration. Multivariate cointegration implies an appropriate VECM can be formed. Same logic applies here as we have seen in ECM. Okay. The criteria for determining the number of flags is AIC or SBIC. And the trace and maximum eigenvalue test for determine the number of cointegrating vectors, whether there is a cointegrating vector, and what means how many cointegrating vectors are there. These two things, based on these two test values, we are going to decide. We are going to assess long-term coefficients and adjustment coefficients. This long-term coefficient, as we have seen, should be -1. And whether there exists a long Granger causality, there should be, if there is a cointegration in, suppose in two price series, then there must be the Granger cause to one series. And then we are going to assess the modal adequacy. So we will go for illustration in R. I think I have taken a lot of time. Okay. Here, whole environment is clear. So we can have a new, I think we'll go for a new script. And then we are going to test all those things. First, with the series which we are going to generate randomly. Whatever I have worked out, I'll see that first, and then otherwise it is going to take longer time. So, yes, this code clears everything. Whatever it is there in your R environment, which you have worked earlier. What we are going to see is we are going to test all those which we have discussed through the randomly generated series. We are setting the seed for random number generation, and we are generating a normal series which we are giving name as
Dr. Purushottam,
yes,
it seems your screen is not shared. Screen of R code. You are showing the screen of R code, isn't it?
yes.
But that is not visible. It's only PowerPoint, it is visible. You have to stop it and share it again. Yes, now it is visible. Now it is visible. Yeah.
Okay.
And approximately how much more time is required?
Half an hour.
Half an hour. Okay. Yeah. Actually, what should we do? Another speaker has come. So should we schedule it later on, or?
It was 1.5 hours. Huh?
But that was 3:30 wala time slot.
Okay.
Okay. So Chandan, like you are here, I think, can you join at 4 o'clock?
Yeah, ma'am. I can.
So you need to, you can be here, you can attend the session, but we'll continue with your session at 4 o'clock.
No problem. Okay.
Okay. Thank you. Thank you. So you can carry on, Dr. Purushottam.
Okay. Thank you, ma'am. So what we are discussing is a different trend process, random walk process, and then testing for stationarity and all. We are going to test it. First, I'm trying to do is generating a random series of 250 numbers, and I'm naming it as a B. So this series, we are going to sequence and make it as a time series. And this is, if we see this, just zoom it. It's a deterministic kind of trend which we can see here. Okay. Then a random walk again, series which we are naming as a Y1. And this is an example of a random walk series, which we have seen in our presentation also. Okay. So we are going to test these two series, whether they are stationary one. So for that, we have to have a library, we have to call the library, or we have to have installed these packages in our R program. So for that, you can install packages. What you can write is install packages, and then you can write name of the package. Maybe simultaneously you can write whatever number of packages you can write like this. Since I have installed these in my system, so I'm not going to install again, but yes, I'm going to call the library. Okay. So I'm going to test for ADF again, which we have generated the series. This one is a series named X, which we generated as a ARIMA module. And then we are going to test whether it is, the series is a stationary one or not. And then results clearly indicates that series is stationary at levels. Another, if there is no unit root, then this kind of different series contains a unit root. So this one, Y2 is not integrated or non-stationary at level. And while this Y1 is significant as this is stationary at levels, this one is non-stationary at levels. If we difference this series, then this will be stationary or will be integrated of order 1. The thing which we have discussed is a spurious regression. Again, I'm generating two different series, E1 and E2. So I'm regressing this X and Y series. One generated from E1, X series generated from E2, and a Y series generated from E1. And then we are regressing this Y on X. We'll see the results. So results show that the coefficient for X is 1.42, though it should be 0, because these are non-related. Significant, highly significant. Then see R square. R square is close to 1. Durbin-Watson test is almost close to 0. So this shows that there is a auto-regression in the series. So another example for Engel-Granger test, again randomly generated series, differenced X and Y to get different series. The code is for diff X, whatever variable, diff, and then the variable which we are going to difference. Okay. And then we are going to test for whether these are integrated of order 1 or whether these are stationary one. Both these series are non-stationary at levels. While first difference is stationary, so we can say this series, both the series are I1. Okay, we'll go for Engel-Granger cointegration test. For that, as we have discussed, we'll regress one series on other.
Yes.
And then we see different, the results. So this results are the long run relationship, which and then we will try to see this residual series. So through this is the name which I'm going to give to the residual series
Mute your
which we have generated from regression. So this one is the
आप कुछ डिटेल्स बताएंगे उनके?
please.
There is some issue in that. Any issue here?
कहाँ पर है? कहाँ पर है?
Speaker.
Any issue?
No, sir.
रजिस्टर में.
With you, sir. Sir, I am speaking to
अच्छा,
मैडम को कहिए वो
आपने मेरे से पहले शेयर किया है इनका?
रजनी मैम म्यूट करवा दीजिए
फर्स्ट टाइम किया.
रजनी मैम प्लीज अनम्यूट योरसेल्फ
ओके ओके.
उनको फोन
अच्छा,
कर
अच्छा,
म्यूट कर
अच्छा अच्छा
ओके
अच्छा. दिल्ली में प्रीत विहार में. ओके, क्या नाम है?
So regression we have seen, error we have generated, configuration we have tested. This
एक सेकंड होल्ड करेंगे.
residuals are once we have seen that residuals are stationary one, then we can say these two series are co-integrated. X and Y are integrated, and the residual series is stationary. We can say that these two series are co-integrated one. Okay, so error correction of these two, again we are going to take, there is 249 100. Yes. Let's see that this error correction term, though it is negative but not significant. Okay. Again, Johansson co-integration. This is again on this randomly generated series. Observations 50E URL. Y1, Y2, two series we have generated. We'll test for trace statistics. This is the result for trace statistics. This test statistics trace test is again higher than 5% critical value. So this one is rejected. We can say that there is more than there is at least one co-integrating vector. Similarly, max eigenvalue test shows that at least there is more than one, means at least there is one co-integrating vector in the series. We can test for vector error correction, whether there is error correction in the series. So ECT, this is not negative, and 0.33 not significant. So that is not correct. I think we will go for another thing. Trivariate one, 3 variables, Y2, Y1, Y2, and Y3. We are combining these 3 series in this through this code, and then we are testing for this one. So there are 3 series, at least there are 3 co-integrating vectors we are testing. The test is testing. So in this one again, only this at least one co-integrating vector is there. No more than one co-integrating vector is rejected. Similarly for max test also, so only one means. So we'll go for the soybean which we have worked out earlier. I'm clearing all the data, and then I'm installing all those libraries, calling my data, which is stored in my file. Okay, so had this is the name of data file which we have given, and these are the series Indore, Ratlam, Devas, Dhar, Sihor, and Ujjain. We are going to take only two series first, Indore and Ujjain, which this you can you can name it like this also, or you can just write Soy, Indore instead of this. Same thing will be there, Indore. So same procedure means we can call it Indore data and Ujjain data. Then we are going to plot Indore, Ujjain, maybe colored one. If we see the plot in right hand side down below. So this is the plot of Indore and Ujjain markets. We'll difference the series. Okay, and then we are going to test for Indore and Ujjain at the level series. So the results show that there is non-stationary at the levels. We'll go for the next different series. So different series is stationary, both Indore as well as Ujjain. So we can say that both Indore and Ujjain soybean prices are integrated of order 1. That was ADF test. We will go for Phillips parent test also. So Phillips parent test for Indore and Ujjain, again, it says non-stationary at levels, while stationary at difference. So both the tests confirm that the series are I1. Okay, so we are going to combine these Indore and Ujjain in one data set. For going for modeling in time series, we can, or error correction or whatever, vector error correction, we need to select the lags. So lag, so this we can say that, and there are criteria AIC or SIBC we have discussed earlier. Any of the criteria we can choose and we can select the lags. Based on AIC, we are going to select 4 lags. Okay. So example for Angel Granger, what we have discussed, we will first regress Indore and Ujjain series, then Ujjain to Indore series. These are the results. And then, as we have discussed in the steps, long run relationship means the regression, and then residual series. Resid we are going to see of the Indore series. Indore regressed on Ujjain. So error we are going to store in error Indore and error Ujjain. So residual series we are going to save in this error Indore and error Ujjain. And we are going to plot this error Indore, error Ujjain, and then we are going to test for cointegration or the stationarity of the residual series. ADF test of the residual series of Indore, ADF test or stationarity of the residual of Indore, Ujjain. So see the residual series from the long run equation is stationary for Indore and as well as for Ujjain. So we can say that these two markets are cointegrated. We are going to test Angel Granger, this error correction mechanism, whether there exists any error correction in those series. So again, different series we are going to take from this soy easy equation what we tested in the data series. We are going to give the name, and then these are the data series: Indore difference, Ujjain difference, Indore difference lag, Ujjain difference lag. And then error series we are going to make it, and then we are going to test for error correction mechanism. So Indore regressed on Ujjain difference series. This one is, we are interested in this one. Okay, as we have seen in the presentation also, though the sign is okay, that should be negative, but error correction term is not significant for Ujjain as well as for Indore as well as for Ujjain. So we are going to go for this Johnson configuration test. Again, we are going to extract the series Ujjain and Indore, combining it, and these two series are combined in SOA MPJ. Lag we have discussed earlier, 4 lags are there. So n-1 lag we are going to put in. This is trace statistics and eigenvalue statistics for Johnson, as we have discussed in the presentation. So integration trace we are going to the name, and function is Kajo. In this library we have discussed in URC or ASTA. These are the libraries for this. Okay. And then we are going to test for co-integration, trace test, and as well as maximum eigenvalue test. This one is the data name, which are going to input. Type is trace. K, as we have seen, lags 4, so n-1 we are going to give. You can put in season also. Since monthly we can give 12, but I'm not giving it. Then error correction term, this configuration, whether it is constant or none. Then specs, whether it is long run or short run. So I'm going to test for this, and this Johnson configuration for Indore and Ujjain markets says that there is at least one co-integrating vector, since trace test is higher than the 5% critical value. Similarly, eigenvalue test, again it says that at least one co-integrating vector is there in the series. So we are going to go for vector correction model, and for that we are going to use the TSDYN library. Okay, this is the library for testing vector error correction. Vector correction, we again take the data series lag 3, and estimation method is maximum likelihood method. So this is the result of this. This one is long run co-integration. Almost all the errors are wiped out within one period. For that error correction term for Indore and for Ujjain. So error correction for Indore sign is negative and is significant. So we can say that there's the correct specification, and this is the error correction. Long run equilibrium is there. We are going to see whether these are error correction terms for that, and then I think we are approaching the time. So error correction, as we have seen earlier, long term and short term. This one is long term and this one is short term one. So this is a kind of, we can see that this price transmission mechanism from one to another. Then diagnostic test, whether whatever model we fit is adequate or not. So adequacy of the model we are going to test. For that, we are going to convert this integrating equation back to, earlier it was in vector term to var. So this is the code for converting back to var. Okay, we are converting back to var. Then we are going to test for serial correlation, and yes, asymptotic, but there is not significant. So there's then RHLM test for heterosidasticity, highly significant one. Then impulse response, how the series are responding to the shocks in another series. So this one is the response of Indore market from the shocks to Ujjain. So any shocks in Ujjain, Indore market also, if any change, increase in Ujjain, Indore market also responding similarly and then decreasing. So this is in the response function for Indore, and similarly for Ujjain also. Variance decomposition, where this is a kind of variance decomposition, forecast error variance decomposition. So this is for Indore series and this is for Ujjain series. Mostly it is affected from its own and partly from another series in both the cases. Okay. As we have seen the series, okay, the Granger casualty also, whether it is Granger cause another series, Indore series as well as Ujjain series. So this doesn't cause, but yes, this one. So if we see this Indore series, means Ujjain series, Granger cause Indore series. Okay, we have taken 1, 3, this Indore as a dependent, and then Ujjain as a dependent and Indore independent. So in this one, there is a Granger casualty. If we see the series, actual series, we see that there is a kind of two type of trends in that. Before perhaps 2014 and after 2014. So this series visually, if we see, it shows that there is a break in or there is a structural change in the series. So we can test for structural change also for Indore, and this shows that there is a potential break point at level 74. At level 74, you can define in the extension. 74 is, okay, this one is 12, mass 12, okay. Similarly in Ujjain, 79, Ujjain difference, we are going to plot these two, difference series, level series. So if we see that if there is any structural break in the series, so this Jevett-Andrew test we have performed, it says there is a break in the series at number 74 in both the series, 74 and 79, I think, yes. 74, 78 in this difference series, 74 in level series in both the cases. So in level series at breakpoint at position 74 in Ujjain as well as in Indore. So there is a structural change in the series, and we have to model accordingly, taking into account the structural change in the series. That's all from my side. Thank you.
Thank you, sir, for giving a very wonderful lecture on the very important topic, market integration. And any question is there from the participant side, please inform us. If there is any query regarding any issue, please inform. Sir, that was nicely explained. So I think queries were not raised by the participants. Thank you, sir.
This shows that either no one understood it or fully understood it.
They have understood, sir. I suppose this thing. Thank you, sir, for your wonderful lecture. Thank you, sir.
Welcome.
Thank you so much.
Welcome. Thank you.
Now we will have another important lecture on AI-based techniques classification using SVM. This lecture will be delivered by Dr. Chandan Kumar Dev. He is scientist in Indian Institute of Agriculture Statistics Research Institute here only in New Delhi. He has about 12 years of experience in research and teaching. He has also received the Nehru Memorial Gold Medal Award for his work, and he has expertise in the area of artificial intelligence techniques. Now I request Dr. Chandan Kumar Dev, sir, please deliver a lecture on the topic. Sir.
Thank you, sir. Thank you so much. I'm sharing my screen first.
Yes, sir.
So, is it visible, sir?
Yes, sir, it is visible, sir. It is visible, sir.
Okay. So before going into my topic of today's lecture, I want to introduce some of the very basic concepts which introduce today's topic. Basically, the SVM belongs to a broad category of subject, that is machine learning, and we can say that machine learning is also a multidisciplinary subject, and the machine learning includes data mining, pattern recognition, statistics, neurocomputing, AI, knowledge discovery, and database. So all these subjects are somehow in one or other way is related to machine learning. So it is very not a very young field, but presently it is getting more we can say that more popular nowadays, but it is a very old field. In 1959, one very accepted definition of machine learning was it is a field of study that gives computer the ability to learn without being explicitly programmed. That means explicitly programmed means we are not explicitly define or describe to the machine each and every situations to the machine, but in part of that we are giving the sufficient amount of data, and machine learn by it own. That's why always the expert to tell this machine learning as a data-driven process. And another very well accepted definition of machine learning was given by Tom Michel. I quote, a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured P improved with experience C, unquote. That means something, some model, some output, some which is machine readable, of course, machine readable part, and that model has the improvement day by day or in any temporal improvement. So so we can also say that machine can improve its performance for any when it get or encounter a new data. So why machine learning is required? Mainly in this picture, we can say that in every situation, these are the apples. Some sort of salad is also apple. This red apple is also an apple. This green apple is also, and this bunch of apple is also apple. This is very clear to the human being, but it is very difficult for the machine to be programmed. See, if we try to incorporate all the conditions of the definition of this apple, and we can define so many and millions of condition to define only one single apple or single object. So from this discussion, this is clear to us that it is not very simple to program all the situation. That's why this non-explicit program came into scene, and we give the machine we program the machine in such way that in a sub-computing way, we are not doing hard computing. We are not including all the situations in which can be used for identifying the object, but we give something to the machine that machine can learn by its own. So in our daily tasks, from waking up from bed to and the end of the day, we are using so much of application, and in each and every application somehow affected by this machine learning or AI technique. So that's why we can understand that how machine learning is important. So why machine learning is also important in agriculture? We can say that machine learning and AI touch every aspects of our life, and agriculture is of course not an exception. We have already seen that machine learning is already been used in soil management, water management, disease detection, weed detection, and it is also used in quality control and quality assurance, speed breeding, and also used in supply demand chain. So what are the basic types of learning system? One is the supervised learning system. That supervised learning system, that means we are giving some supervision to the machine in form of data, and machine take that supervision to understand the data, and ultimately it will produce some model. And another type of learning is the unsupervised learning. Unsupervised learning, where we are not explicitly say to the machine that this is your class, or this is the level of your class. Machine itself try to learn what class it should like this object should belongs to which class. Another very important is reinforcement learning. Reinforcement learning, what in this reinforcement learning does, the programmer gives some kind of award to the learner, so that it can automatically guided by that award, in which direction it should go to learn. And another is semi-supervised learning. It is the combination of the supervised and unsupervised learning. Some of the objects need to be leveled, and other objects are not leveled, and this type of learning is semi-supervised. And recently, another type of learning is also getting popular day by day. That is self-supervised learning. We need to only give the data to the machine, and some kind of specialized algorithm will learn by itself. So in supervised learning, what it does, if we take some example of male classification, that male classification means whether this male is harmful to you or not. That classification is spam, and that harmful male, the name of the harmful male is spam, and on the other hand, the male which are not harmful to, generally called ham. So what are the training say to do? We literally handcrafted the male first for the training purpose, that these males are spam and these males are ham. Okay. So these are the spam, and these are the this total training set is used for the training. But after learning, in this part, we can say that the learning process done, and after that learning that whenever the new instances come to your mailbox, it will automatically identify whether it should go to your inbox or not. And some of the supervised learning algorithms are k-nearest neighbor and linear regression, logistic regression, support vector machine. This is our topic of discussions today. Another supervised algorithms are decision tree and random forest and neural network. Some of these algorithms are also very much capable of doing unsupervised and reinforcement as well as semi-supervised learning in some tweaking in the programming. So semi-supervised, what is semi-supervised? If it will be clear from this example. Suppose we all are using Google accounts and we have Google Photos, or we have the Facebook accounts. Whenever we upload some photos, Facebook automatically suggests whether you want to tag this person or not. So how this can be done? See, in first place, whenever we upload something or post something, sometimes in our timeline we may have tagged someone, and this, suppose we have 100 photos of particular of my friend, and that from that 100, 10 photos is already tagged. That means that label is done for the 10 photos and 90 photos is untagged. That means it is some sort of semi-supervised. So that whenever the new instance come to your system, and machine will capable of automatically identifying the images. So that kind of things are belongs to semi-supervised learning. And another is unsupervised learning. Unsupervised learning is it depends on your data, and you have to give how many category you want. Suppose this is my training set, and I want some 4 category from my training set, and it will automatically try to aggregate the similar category object to a particular cluster. So this unsupervised learning is also known as clustering. So our today's topic is support vector machine, and this support vector machine is of course a classification technique, but it can be used also for the unsupervised learning. So some of the unsupervised learning algorithms are k-means algorithm, hierarchical cluster analysis, and EM, expectation maximization. So fourth category of the learning is your reinforcement learning, and as I said that in reinforcement learning we try to give some award or punishment to the agent. Agent means the computer program which try to learn from the data. And in this situation, what the agent does, it takes some action. On the basis of that action, it gets some feedback in terms of reward or the punishment. If it gets some rewards, and then it is an indication that it should follow that path. And if it is getting some punishment, then it will not take that part. It is generally like how a child learning to walk. So this animation can be used for this reinforcement learning. In reinforcement learning, suppose this agent is collide with this beam, and it gets the negative reward. Then automatically it will try to jump whenever it encounter the beam. So in this way, the reinforcement learning come. That reinforcement learning is used in the gaming industry as to make the player or automatic agent to be more expertise to the automatic agent. So the question is, whenever we're talking about the machine learning and this part of the AI concept, the problem is what is the data format. So this can be this can be think of like a table. Yeah, this is the data, and this is the features and the level, and how tabular format has two things. One is column and another is row, and that row is the instance of to the machine, and the columns are the features to the machine. Some of the literature suggests that whenever we are taking this column name with the data, it is called features. And some of them, this only the values of the values of the column is called the features. So if we think of this classification technique, that is the supervised learning, here the last column is used for the supervision. That means if we have the column name F1 to F4, and these have the values from 4.1, 3.0, and lastly the 0.2, and it level is something like Virginica. So this is the format, and some new instance, whenever the new instance come, and on the basis of this value, the level will be different or the same. So this level will gradually guide the learner to learn that if our data is this kind of value and this kind of combinations in the attribute, then the level will be this. So so this is the tabular format for the machine learning purpose. How the image data is used? See, we can think of this image data like this. And we can convert this image data in the tabular form, then we can feed into the machine learning setup. Okay, so that is the primer of this today's discussion. Now we will see the support vector machine. Support vector machine is came into this academic industry in 1995. It was developed by Vladimir Vapnik, and firstly, initially it was used for only two-class classifier. But generally what happened, this support vector machine became very robust in different situations and different problem solving situations. Like generally support vector machine, initially it was two-class classifier, then it became multi-class classifier, and after that it was started using in clustering. So gradually its power was increased day by day. So why it is support vector machine is important? Because unlike regression, it is very well work on linear and non-linear classification, and even in outlier detection. So as I said, that support vector machine can also be used in the clustering purpose. That is, means we can also use this for the unsupervised learning. So support vector machine, unlike artificial neural network, it is well suited for the small or medium-sized data, but it can classify the object in very complex situations. So we can say that in many situations, the computation, if we compare the computation as well as the other factor, it outperforms the other machine learning techniques like ANN. So before this era, before this GPU or TPU or the deep learning era, and the support vector machine was started outperforming the ANN. So okay, so the basic principle of the support vector machine is we can say that we classify the object in a space. Suppose one three-dimensional space is there, then we want to classify our object in that three-dimensional space into two different classes. Then we need one hyperplane that is two-dimensional. So what here it is describing, that means if our data is n-dimensional, then only n-1 dimensional hyperplane can be separate that n-dimensional space into two classes. In this manner, the support vector machine is used. But the principle is whenever the hyperplane is try to set in such a manner that the two class have the maximum margin to that hyperplane. So in that aspect, that support vector also came. We will see in the subsequent slides. So if we think this, these are the support. This is the principle of support vector machine. Support vector machine. That principle says what if we want to linearly separate our data into two classes. One is black solid class, another is black hollow class. And some of the lines, this linear, we can say that this is the line what actually machine learned from the data. But there are three lines that green, blue, and red. We can say that this red line is more efficient than these two lines, because this green line is not at all separating this solid black and hollow black class. But in case of the blue line, it is separating, but it is not maximizing the distance between the two classes. But in case of the third classifier means we can say that here our data is in a two-dimensional space. Then we our one single line can separate this two-dimensional space data. So this H3 hyperplane, here the line is hyperplane because our dimension is here is two dimension, and line is separating our data. So this is the most efficient classifier here. So this is the thing basically, and in this line, this black line is the classifier, and we are trying to maximize this road, and these objects are which are residing in the edge of this road are called the support vector. Support vector, that means it is supporting that it is the last object of this particular class, and this is the last object of this red class. So if we are take this example in three-dimensional space, before that we have seen that that line can separate that two class. Here one plane can separate that two class. So it is three-dimensional picture. That's why that support vector is not very well seen, but support vector is the closest object which is residing in the edge of the road, and we are trying to maximize that road. That maximization of this road basically make this classifier more generalized. Why it is more generalized? Because whenever the new objects come to you to classify the new object, whether this new object belongs to the red class or the green class, then it will help whenever the that maximized road is there. So this support vector machine can be used for the linear classification. Some of the observation of this two pictures, that is two. Here we can see that the two class can clearly be separated easily with the straight line, that is linearly separable. Sometimes it depends on your data, that whether your data is linearly separable or not. On the basis of that situation, you can use the technique which is suitable for your data. Here I have segregated this left plot here, and here it is showing the three possible classifier, and here the same situation which were in the 3D picture, and before that we have seen that this dashed line is not at all classifying the objects. But two other classifier is trying to classify the boxed blue and the yellow objects. But these are not good at all, because of the boundary. Whenever the new object come to this classifier to classify this, it will not be able to properly classify that new object. But in case of this right side plot, it is basically what is describing. It is describing that the wider road. That means here our classifier is there, and the first object of this class is very far from this road. So that road, difference, that wide road is more generalized, because new object can be classified very well. So how white like road is help to your classification. Adding more training instances of the street will not affect the decision boundary. Suppose more object come to this. Here it is a new object for fall into this portion of the road, but still it is left side of your classifier. That means we have more space to put our new object, and it will classify easily of the new objects. So another two concepts are there for support vector machine, and that is the soft margin and the hard margin. Soft margin means it is what it will do. It strictly impose that all instance be off the street and on the right side. That means our decision boundary is very stiff, but that hard margin, sometimes it is very difficult to learn the machine, that whenever the outlier is present, because whenever we are using the hard margin, it cannot classify properly the outliers. So for avoiding that situations, uh, the the solution is we can use the soft margin. That means some kind of flexibility will be there in the margin of the support vector. So it can vary in situations to situations, that it depends on your data, and sometimes you have to keep good balance between the hard margin and soft margin. So okay. So this is the two situations that whenever here the hyperparameter, the C has been described. This is one of the important hyperparameter in support vector machine. This was also incorporated in the machine learning package, that is sklearn. So whenever the hyperparameter is low, we will get the wider road, and whenever the hyperparameter C is large, then we will get the smaller road. So that border of the road, that means width of the road should be wider in such a way that your classification should be done in proper manner. So that was the linear classification whenever your data is linear, but it can be used for your nonlinear classification. How we can add some features. Suppose our data only have single variable, that is your x1, and in case of this, we cannot linearly separate this data into two class. So that's why what we can do, we can transform these green features into we can put squares of these green features. Then automatically it will plot like this, and this separating line can separate these two objects into two class. So that is one way to the classification purpose. So I have told that this SVM can be used for supervised learning, as I discussed, and unsupervised learning, and SVM is also can be used for the regression purpose. So it was not in the initial phase of the of SVM, but generally it came into the SVM. So every time this SVM regression is like it will predict like the linear regression, but it is sometimes it is more efficient. It depends on the data complexity. So for SVM regression, in case of the SVM classification, the hyperparameter was C. Whenever the C is smaller, then the wider road we get. But in case of the regression, the hyperparameter is the epsilon, And this epsilon, if it is increased, then the wider path wider road we will get, and the classifier. And in case of the regression, the concept is little reversed, because in case of the classification, we are trying to separating the two class as wider as possible. But it's in case of the regression, we are trying to put the objects in on the road. So whenever the regression, because in case of the linear separation, we can use this epsilon hyperparameter only. But in case of the polynomial case, polynomial data, which is not linearly separable, so we can use some polynomial degree to the classifier, so that ultimately we get some model that is capable of identifying the new objects, or giving the prediction for the new instances. So support vector machine, whenever we are using that support vector machine, we can tune the parameter. Tune the parameter means in every machine learning situations, depends on your data. We have to tweak some of the your parameters available in the algorithm. So one is the margin. We can widen the margin, or make it smaller. Make it smaller for your particular data. It depends on your data, basically. How can we identify that whether our margin width is correct or not? In our Python implementation, we can see that we have some methods to identify the performance of our machine learning method. So in that case, we have to identify the particular margin width. In case of the SVM classification, we will select the C, and in case of the SVM regression, we will select the epsilon. By that, we can widen the path. So this is the regularization, and that gamma means I have seen. I have told that whenever that means this gamma and kernel both gives the classifier the non-linearity. Whenever the non-linear linear situation is there, that kernel and gamma is used to cope up with that situations. So support another very important concept of this support vector machine is kernel trick. What is that? We cannot explain it in the mathematical way in this class, but we can visualize this. Suppose this is our data. This is two class. One is the blue cross, and another is the red hollow class. But it is difficult. What kind of classifier can classify these two class? But if we see this data in 3D views, then we can easily identify there is a difference between these two class. So basically, what we are trying to do, we are just trying to increase the dimension of our data to actually see the segregations of our data. So here it was the data so what was that kernel trick is? Kernel trick is converting this two-dimensional data or seeing this two-dimensional data in the three-dimensional space, so that we can identify the separation line. We can say that whenever the three-dimensional space is there, we require one hyperplane to segregate these two classes. So this is the mathematical representation of this decision class. It is 3D model. One here, two classes there. One is blue box, and another is green triangle. And what the decision boundary? How the decision boundary is identified? This is the function. Basically, H is the function, and this is the WTX plus V. Actually, this is the kernel function which has the capability to segregate these two type of objects here. So this and how machine learns, we have this X and we also have this H. But whenever we give the training instances of X and H, it will automatically identify the WT and V. Both are the metrics. So we can also implement this in the two-dimensional space, three-dimensional space, as well as the multi-dimensional space. In this case, this function, this discriminating function can discriminate the objects into two class. Here, this hyperplane can be made through this. So this function also like make this middle of the line, and whenever it become plus or minus 1, it will fall on either side, and whenever it is 0, it is fall on the line. So in this way, the SVM segregate the objects. So some of the applications are there already in different industry. The support vector machine has been used, that is face detection and text or hypertext categorization, classification of the image, handwriting recognition. So but I want to share one of our experiment in where we have used the SVM classifier. And the situation was like that. I think, sir, data is seeing, na? Data is shown to you. Sir, Excel file is showing or not? Sir, Excel file is visible?
Yes, sir. Yes, sir. It's visible, sir.
Okay, thank you. So what was the experiment, and I hope it will give some idea in your own field to implement this SVM. So it was experimented in NRC Orchid Pachyong. There dendrobium, and we know that the orchid plants are very less, and it is very difficult to destroy even a single leaf to calculate the phenotypic behavior. So what we have done, we have used image J to identify the length and width, and also use the image J to identify the area of that leaf. So accordingly, we have collected around 1600 individual leaf images to experiment this, whether it is it is possible to predict the area of the dendrobium leaf on the basis of your leaf width and leaf length. But here it is not saying the leaf width and leaf length. It is the cubic of this leaf width and leaf length. We can also here for showing this one particular program I have taken this example. We can also take the actual length and width. Some transformation was done to see whether any changes is there, any changes happen or not. So this is about the data, and okay. This is the experimental code. I can also share the generalized code with you if it is required. So what we have done, we have experimented in Python, and this pandas and pandas was imported, and sklearn. Mainly we have used this sklearn package, and you can also see this sklearn package has a rich documentation. That means in sklearn we can use you can have the code of classification, regression, clustering, as well as dimensional tree detection, model selection, pre-processing. Many things are there, and this is available. This is freely available, like the other packages of Python. And from this documentation, we can use this SVM, and all the codes and concepts and all the things you can have from this. And this is the SVR. In our situation, this SVR, this SVR also. SVR was used, and that is for the regression purpose. How SVM can be used for the regression? We have taken some of the suggestion from this documentation, and we have implemented that part into this. What we have done, we have first we have collected collected that data and put it into one CSV file. And then what we have done, we have simply dropped the leaf area level, so that we can feed machine only the width and the length. And the actual level means in our data description, I have told you that that levels part help us to actually classify. Actually, it is the supervisor to our machine learning algorithm, and to tell that if the features is this, then the level should be this. So in this way we have divided our features and the level into different variable X and Y. We have to reshaping it for the actually the API readable format, make it API readable format. After that, we have the two sets. One is the training sets, and another is the validation sets. Mainly in machine learning, what we have to do to identify or to calculate the performance of your method, you have to split your training data into two parts. Rather, presently it is three parts. One is training, and there is validation, and third part is testing. But in our case, we have segregated our data into two parts. One is the training set, another is the validation set. Then we have used this training testing split function to split that actually what should go for the train and what should go for the test purpose. Then what we have done, we make one support vector regression pipeline. This is the standard procedure. If you want to use this, you can simply use that code to make it a standard standard scalar. And SVR, I have used the epsilon 1.5. This is a matter of experimentation. We can change the epsilon to make the road sometimes wider, sometimes make it shrink. So after that we have to fit the model. Fit the model, that means this line, this higher level API is very powerful, and that we need not write a explicit code to train our model. Only what you have to do, you have to simply initialize your model to some of the parameter. Here we have previously tested that our data is very much linear, and we can use that linear separation. So we have only used that epsilon parameter. After that, we fit that training for X and Y. X and Y means the features and the labels. And then we have used that model, which has already been trained. That is support vector dot fit means all the learning process will go into this support vector VR. Then what we have done, we have used the Y parade variable to predict whether it is working fine or not. Then some of the performance metrics, I believe you all know that performance metrics, that is mean square error, and after that that mean square error, we have taken out the square root of that mean square error to identify the RMSE. And okay, then what we have done, we have done some kind of cross validation. Why cross validation is required? Cross validation is required because by single training we cannot confidently tell that this model is sufficiently generalized, so that we have done 10-fold cross validation. After that, we have predict, and again we have identified some of the matrices. Then we will try to identify whether our machine is. This is the result. This line is for actually representing whenever the measured and predicted area is same. So here we can see that our model is here, R squared is 0.95. That means model is almost 95% correct. So it is not the end of the story. There is a chance to improve this model by tweaking our hyperparameter. So this is one of the experiment, and which can be used for this. And okay, I think this is not required now. I I have already discussed that part. So that is from my side, sir. So any questions?
Sir, thank you, sir, for your lecture. I am now requesting the participants, if you have any query regarding the issues, please inform us. Through chat box also, you can inform your views. I think no issue is raised. So at the end, I thank Dr. Chandan sir for delivering such a good lecture on a very important topic, which is a very futuristic topic also. Thank you, sir, for your lecture.
Thank you, sir.
Thank you, sir.
Thank you so much, sir. Thank you, ma'am.
Thank you, Chandan, for agreeing to deliver this talk. In fact, I wanted to personally attend the whole session, but some meeting was there, so
yes.
I could not attend it. But I would definitely see the recorded version of it. So thank you once again. Thank you very much.
Thank you, ma'am. Thank you.
Thank you. So close कर दें?
जी मैम, अब तो क्लोज कर सकते हैं अगर कोई इशू नहीं है तो।
ठीक है। अच्छा, एक बात थी विकास जी, कल ये लोग 10 बजे ज्वाइन करेंगे, उसमें